Let's talk about Zener diodes. We've already looked at switching diodes, so we understand how those work. One of the things we took note of when we were looking at switching diodes was that if our reverse bias voltage is too high, then those switching diodes can fail. Specifically, the large reverse bias voltage can cause the PN junction to fail catastrophically and irreversibly, meaning there's nothing we can do and the device is destroyed. But it turns out that there are some diodes that are designed to repeatedly enter and leave the reverse breakdown region with no ill effects. It turns out that there are two physical mechanisms that allow this to happen. One is called the Zener effect. That's usually in play up to 5 or 6 volts or so. And then after that, for voltages greater than that, it's a mechanism called avalanche breakdown. No matter which mechanism is in effect these days, we tend to call the diode a simple Zener diode. The symbol for the Zener diode looks like a slightly decorated regular switching diode, where there's just a couple of extra lines on the cathode end of the symbol. Now, when the device is forward biased, so the anode is greater than the cathode, the device behaves just like a regular switching diode. And so for silicon devices, the diode won't turn on until the forward bias voltage is about 0.7 of a volt. In reverse bias, things can be quite different. So for reverse bias voltages less than the reverse breakdown voltage, the diode will be blocking. When the reverse bias voltage exceeds the reverse breakdown voltage, it will go into breakdown voltage, but you can happily take it out of breakdown as well. It turns out that that breakdown voltage can be precisely controlled during the manufacturing process, and it can be from just a few volts up to well over 100 volts. If we want to explore the terminal characteristic of a Zener diode, we have our usual test circuit like the one shown here. We've got a variable DC voltage source on the left hand side, VB. VB can be adjusted so that it's negative or positive with regard to the reference. The Zener diode D is connected to the voltage source via the current limiting resistor R. And if we measure the voltage across the Zener diode, we'll call that VZ, and the current through the diode IZ. And what we do is that we adjust VB over a range of values, and then for each value of VB we record IZ and VZ and then plot those points on a graph, and that will give us the terminal characteristic. So here's the terminal characteristic for a typical Zener diode, and you can see a few interesting things. First of all, the forward bias, sure enough, looks just like a regular silicon diode, where the device turns on at less than 1 volt and conducts with a very high value of conductance. In the reverse bias direction though, the diode appears to be breaking down at a much lower voltage than one might normally expect. In this case, it's breaking down around about minus 11 volts. But the key point is that we can take this diode out of the reverse breakdown voltage, provided we're not exceeding any of the manufacturer's maximum operating parameters, such as the maximum current through the device when it's in reverse breakdown. The voltage VZK, the Zener knee voltage, is the nominal voltage specified by the manufacturer. So we would have picked this voltage, this Zener diode, because it's got a reverse breakdown voltage around about the value that we're interested in. Now, the reverse breakdown region, the knee as it's called, is very sharp, and when the diode is in reverse breakdown, the conductance is very high. So IZ can vary quite significantly while in reverse breakdown, but the voltage across the diode, VZ, will be tightly constrained. It won't vary very much at all. And so one of the main applications of the Zener diode is to connect it up specifically in reverse bias and then use the very small variation in the Zener voltage as a function of Zener current to act as a voltage reference. So that leads us to a couple of very simple models that work very effectively for the Zener diode. So the first thing we do is that let's just agree that from now on we're going to measure the Zener current in the reverse direction from the cathode to the anode, and we'll measure the Zener voltage Vz also from the cathode to the anode. So sort of going against the convention that we use predominantly for switching diodes, mainly because most of the time for the things that we're interested in, the Zener diode is going to be reverse biased. So the knee voltage is very sharp and the conductance in reverse breakdown is very high. So to a first order approximation, the Zener diode in reverse breakdown looks very much like just a battery. And the terminal voltage of our model battery is VZK. And in this case we're taking no account of the voltage drop across the bulk of the silicon in the Zener diode, and instead we're just modeling it as a simple battery. It's amazing how often this model is perfectly okay for our calculations. To have a slightly more sophisticated model, the sensible thing to do would be to include the non-infinite conductance when in reverse breakdown. And that's very easily taken care of by just including a small series resistor with the Zener battery in the model. So as you can see here, the real Zener diode is now being modeled as a battery voltage with terminal voltage VZK in series with a resistor RZ. And now the total voltage across a Zener diode is given by this series combination of VZK, the knee voltage of the Zener diode, and this extra term IZRZ, which clearly goes up as the Zener current increases. And this accounts for the fact that when in reverse breakdown, the conductance of the diode is not infinite. Now, this diode model is slightly limited in the sense that we're not even trying to model the forward bias behavior of the device, but that would be very easy to include one of our forward bias models from the material that we looked at on switching diodes. A typical application of the Zener diode is as a voltage reference. Now, a voltage reference is a circuit that produces a very stable and known voltage, and it's used in many other circuits. There are plenty of times where we need to have a precise reference for other parts of our electronic circuits to work. Why is that? Well, we can't rely on the power supply voltage. For example, if we have a portable device which is powered by batteries, we can't rely on the battery voltage being a constant voltage, because the discharge characteristics of batteries show that they're amazingly variable in their terminal voltage over time as the batteries are discharged. If we needed to use the circuit, for example, as part of an analog to digital converter, and we want to be able to calibrate the numbers that are coming from our ADC, we need to know what voltage is actually being digitized by the ADC. So we need a known reference voltage. Similarly, if we're trying to convert digital output into an analog voltage, in order for us to get a known analog voltage, we've got to have a reference against which our circuit essentially calibrates itself. And also, if we want to create a voltage regulator, then we need a voltage reference as part of that, and we'll see that in a minute. So voltage references can be relatively simple, or they can be considerably more sophisticated. So this would be your entry-level voltage reference, and there's really not much to it. So we've got the power supply voltage VCC feeding the Zener diode via a resistor R. Now we choose the value of R so that the Zener current IZ is sufficient to ensure that the Zener diode is in reverse breakdown. And when it is in reverse breakdown, we know that VZ could be modeled by our simple model 1 with the battery equal to the Zener knee voltage. Now we've got a unity gain buffer here. The op amp is providing buffering. That's so that the whatever is connected to Vref doesn't unnecessarily load the Zener voltage, because we know that in reality the Zener does not present a perfectly constant voltage, and the operating point of the Zener voltage of the Zener diode will change slightly depending on how much current we are drawing away from that biasing network involving R and the Zener diode. Now this isn't the greatest circuit in the world. As I said before, VCC could be varying quite a bit. It may come from an unregulated source like a rectifier, something like that. So this isn't the best circuit. A better circuit would be something like this, where we bias the Zener diode from a current source. So regardless of what VCC is doing, if we insert a current source, then that ensures that the Zener diode bias point is stable, and we include the op amp buffer still to ensure that no current is drawn away from that biasing network. So you can see this is very straightforward. There are a few catches that we haven't included in our model. For example, there's a non-zero temperature coefficient in the Zener diode, so as the temperature changes, the actual reference voltage is going to go up and down. But you can buy other more sophisticated reference circuits. You may have heard of band gap sources, so they include extra silicon devices so that the temperature coefficients of the internal components essentially cancel each other out, and we can have a very stable voltage over time and temperature. The voltage reference is used in a number of circuits. You can buy them as complete integrated components now, but this is the basic idea behind them. Another major application of the Zener diode is as a voltage regulator. Now, a voltage regulator is usually part of a power supply. The power supply via a switching diode regulator and a filtering network provides an unregulated DC output. The regulator then takes that unregulated DC output and turns it into something stable. So the voltage regulator maintains a stable output voltage, and ideally we want it to be insensitive to variations in the input voltage, right? Because the input voltage is going to vary if it's being fed from an unregulated source, and also the load current. So if our load varies, depending on what the circuit is, that's extremely likely. Then we want the voltage regulator to keep a constant output voltage. Voltage regulators themselves can be extremely sophisticated, and we'll have a look at some of those when we look at applications of transistors. One very simple voltage regulator for very low power applications can be as simple as this. So on the left hand side we've got an unregulated voltage source Vs, and just to be clear, an unregulated voltage source means usually in electronics that it's a DC supply, but it varies significantly. So for example, it might be a DC supply, but Vs might vary from 10 volts to 14 volts. Right? So we call that unregulated. Now the resistor Rs and the Zener diode D form the regulator circuit. The load, which would normally be some extra electronics, is represented by a single load resistor RL. And we connect RL across D, and we rely on the Zener action to keep the voltage Vz fairly constant, and therefore the load voltage VL will be constant. Now even though this is a very simple circuit, there's a few subtleties involved, particularly if the load can vary from say, a very large value of RL to a very small value of RL. For example, we know that we have to have some minimum value of IZ flowing in the Zener at all times in order to keep the device in reverse breakdown. That means that no matter what the load resistor RL is, we have to ensure that that minimum current, for example it might be 20 milliamps, is flowing in the Zener diode. Also, when we remove the load resistor, the load current is going to be added to the Zener current, and so we have to make sure that the Zener diode has a high enough power rating to take that maximum current that's going to be flowing. And you can also see that the current IS is going to vary. While the Zener diode keeps the voltage VZ approximately constant, remember VS is unregulated, so that goes up and down. That means that the voltage across RS goes up and down, meaning IS goes up and down. So these are all factors that you have to consider when choosing the value of RS, choosing the power rating and current rating of the Zener diode D. Now, in reality, these circuits wouldn't be used very much. We would probably buy an integrated voltage regulator, but at a pinch, for the right sort of application, this will do fine for, like I say, very low power applications. Later on, we'll have a look at transistor versions of this, where there is some feedback. The presence of the transistor allows us to have much larger load currents, and we'll have a Zener source providing voltage reference for a much more sophisticated voltage regulator.